Hey, what's up, guys? Chung here again. And so this time I want to discuss with you guys about this week's contest hard problem number 1553, minimum number of days to eat n oranges. Okay. I mean the description of this problem is pretty easy, but it's kind of tricky. It's it's a hard problem anyway, right? Okay, so let's take a look. What does this problem is asking us to do here? So there are like n oranges in the kitchen, and you decided to eat some of these oranges every day as follows. Okay, so eat one orange. You can on each day you can do the followings. You either do eat one orange, or uh, if the number of the remaining, basically if the current oranges can be divided by two, then you can eat half of the oranges. Basically, you have a half of the oranges left. And if the number of remaining oranges is divisible by 3, then you can eat like 2 times of the 1/3 of the oranges, which means you can have like 1/3 of the oranges left, right? And you can only choose one of the actions per day. Return the minimum number of days to eat n oranges. Okay, so mm, but here's why this problem is a hard problem, because the constraint is huge. See, n is even greater than 2 times 10 to the power of 9, which means we cannot even use a linear. Basically, with this like many like data, even the O of n algorithm will TLE. Okay, so for this one we have to use basically log n or the constant, right? Okay, so how can we do that, right? I mean, how can we do it? I mean, as you guys can see, return the minimum number of days to eat an oranges. Like I said, every time we see a minimum, there are like a bunch of options we have here. I mean, the first one is okay, so this one can be used, this problem can be solved with DP solutions, yes. And basically, we will also be talking about the DP solutions later in this video. But with these minimum numbers here, I mean, a few things maybe you guys can think of, right? The first thing is like, can we do the first one is always the Bfs search, right? I mean, every time when you guys see some minimum numbers here, and you see a bunch of options at each step, I think the first things you guys might want to try is do a Bfs search, because Bfs search is to find the minimum path. In this case, it's undirected graph basically, right? From one node, you have 3 options here, okay? And we need to find the minimum like steps from one state to another. In this case, which is from state n to state 0, right? Because we want to eat all the oranges. Okay, so how about we try to solve this one with the BFS, okay? And the BFS is as this, right? So the BFS, we will have like template, which is we're gonna have like the queues first, right? The queue equals to collections dot DQ, right? And the first state is n, okay? And then we're gonna have like a scene dot set, right? Set, and the scene dot add n, okay? And then an answer here, of course. We're gonna have an answer here equals to 0, okay? While q, right? And let's do a for in range length of. So what I'm writing here is just like a regular BFS template, okay? Q, right? So here, every time we have a current number, or I can call it a node here, whatever. I will call it current number here, okay? And queue dot pop left, right? So with the current number, how many options do we have here? We have three options, right? The first one is the basically if the current number can be divided by 3, right? And then we do what? We simply uh, do a queue dot append, okay? Right? Basically, uh, eating two-third of this n means we have 1/3 left, right? So after eating this many oranges, this is the oranges we have for the next loop, okay? And then the next solution will be this, like n2, right? If the number can be divided by 2, then we append n divided by 2. And the last one is this, right? I mean, um, sorry, uh, and right, the BFS template not in scene, right? Scene dot add, okay. So same thing for this one, right? So we only append to the queue when this node has not been seen before, okay, right? And there's always like another one, right? Basically, if the current number minus one not in scene, not in, right? So here this is in here. This is also a in, and then we do a queue. Okay, I'll just copy this one here. Here. I think here should be a current n, right? Sorry, not this one. Current n. Everything is current. Okay. 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 So, and every time we just simply do a +1, and then we simply return the answer here. Okay, I think someone may have already may have some raised some questions here. I mean, okay, we are adding this current -1 in append to the queue here. Wouldn't that like timeout TLE in this case? No. Why is that? Because we will. Okay, sorry about that. I haven't write the exit conditions here. Basically, if the current n is 0, we simply return the answer, right? Else we return -1. Yeah, let's try to run this code, and I always explain why it will not TLE. So it passed, and it's only running like for only 100 milliseconds here. So why is that, right? Let's say we have a huge number here. Let's say 10,000. Okay, it seems like we will be like doing like a linear search, right? But the problem is it's a but the number of the basically we will have a tree here, right? Because we have those kind of like a 1/3 of the number or half of the number here. So the total while loop here is bounded with the log 2n or log 3n here. Basically, it's bounded with log n. So even though we have in the current queue, let's say every time we'll have like an additional uh, item, additional node into our queue. But once that is popped out, the next one, I mean, so basically this is something like let's say we have a one 10,000 numbers here. I know, so every time we'll always have this number in the queue. Basically, the first time we're gonna have like 9, 9, 9, 9. right? So the first time we'll have this, and probably we'll have like some other numbers here, maybe some smaller numbers, okay? And then from 9999, right? From 9999, it's for the next while loop here. Of course, this is let's say the day one. For on day two, so we'll also have like a 9998, right? But in this case, on day two, besides 9992, we also have like 3333, right? Because now the 9999 can be divided by 3, right? So then we have this, right? And then on day three, what's going to happen still, right? Since we're going to process all the nodes in our queue here, of course, this one will be like 99997, right? Makes sense, right? So it'll be 9997, but I know, so this one basically the first one will always be like linear decreasing here, but we will not be yeah, scanning all of those numbers because we have this like much smaller numbers going on here. Basically on the third time, right? See, 3333 will become like 1111, okay? And this one will of course like 99996 since this one is always not there, right? Now the 1111 will become it cannot be divided by 2 or 3. Yeah. So this one's gonna be a 1110. Okay. Let's keep going. 9995. How about now? Here we have two options, right? Since this one can both be divided by 3 and by 2. So we're gonna have like this one by 3 is the 321 3 yeah 330. Okay. And if we divide it by 2, it's going to be a 550. Okay. So that's the day four. Maybe I'm assuming I'm just counting this one like randomly, right? So the fifth day, I know. So this one will become 99994. But here, right, it's gonna be keep decreasing like exponentially, right? This one's gonna be 35. This one is gonna be a 2 like 75, right? I think you guys have understand, right? So even though in our current queue, there's always this like a long decreasing list here, right? But this number, right? This number will be like calculated later on. I mean maybe I think here it's like 99994. Sorry, I think I should have like this is not the correct like op all the numbers here because for 9995 maybe this one like for example 9994 this one can be divided by 2. Maybe it's like this is like 27 plus 5 32. Maybe this one here. So from 9996 and 1110 this 9996 can also be divided by 3, right? So besides these three numbers, we'll also have like a 3332. Okay, right? I mean, what I'm trying to say is that even though like we'll always have like this linear decreasing numbers here in this queue, but will meantime we'll also have like many more much smaller numbers, right? Decreased by a third or by a half or even by a third, right? So by keeping this one in the queue doesn't really hurt us too much. It's just adding some additional loops by the number of basically by the height of the tree here. Mm, yeah. See, so that's why these things will not causing us any TLE here because the remaining numbers will give us basically will end this while loop in a much earlier time. So while this thing will just be a huge numbers, but we don't care. As long as any of those conditions, any of the candidates in the queue has reached 0, then we're done, right? That's why this a BFS search works. I mean, to be honest, I think as the last hard problem in the weekly contest, and if you're solving this problem with this BFS search, I think it's like a little bit easier than I anticipated. But even for this BFS search, the tricky part is I think it's a tricky question for all the BFS search, unless the question itself is so obvious that you don't have any other choice but to use the BFS search. For all the other problems that can be solved in a BFS manner, is that you have to be able to convert this problem or transform this problem from the description to a BFS template. So what are the some features or the characteristics of a BFS problem? First one, then the most notable one is it asks you to find the minimum value. So of course, as you guys can imagine, right, the BFS always help you to find the minimum answer. So the first one is the minimum answer, and the second one, how about the second one? The second one is you have a starting point. In this case, it's an n, and you have a clear ending point. In this case, it's 0. As you guys can see, because for the BFS problem, you have to be you have to define like a base condition where you need to stop, right? And in this case, the starting point is the starting state is n, and the ending state is 0. I think this is the part many of you might have overlooked maybe. Maybe even though like let's say you see okay, so there's a minimum numbers here, but is this really like a BFS problem, right? Then you have to be able to see the pattern here. So from n to 0. And the last one is from each of the state, you have few options here. Okay. And in this case, it's hmm, it's 3 options here. So comparing with the BFS search, how about the DFS? So what's the characteristics of DFS? I mean, many other problems can also be solved by, besides DP, can also be solved by the DFS. So the DFS is basically trying, all the possible paths. Okay, and then after like trying all the paths, right? And then you can basically you either get the minimum value or the maximum value of that. I think the characteristic for the DFS search is it's the same thing, right? And for the DFS search, we usually use like the recursion, the recursive method, right? And for the DFS, so what are the other like uh, characteristics for the DFS search? So first thing is I mean, for DFS search, it's a directed graph, where for the BFS it's undirected. Because for the DFS search, since we don't have this like scene set here, basically from DFS, you can only traverse coming from, let's say, I minus 1 state to I state. Okay. And then for DFS search, usually there isn't like a fixed state, the final state here. And yeah, because mm, yeah, or like for DFS, right? For DFS or it's not asking you to find the minimum number of days, not the minimum number. Or for example, maybe it asks you to find the total different path, right? Or different ways of doing that, right? And then you can just also use the DFS to solve this problem. But at least for this one, it's a very good candidate of using the BFS search. it has all the characteristics for the BFS. The start date, the end date, the different options for each state, and ask you to find the minimum of the path. Cool. So that's the Bfs search. And I promised to you guys to uh, for the DP solution. Okay. So let's take a look at the DP solution here. I mean, I think the DP solution is it's more difficult than the DFS than the BFS here. And okay, so for the DP solutions, I mean the first things you guys might have come about is like the top-down solutions, right? So let's say we have DP DPI, right? DPI basically. DPI means what? It means the minimum, right? The minimum. Sorry. Oops. Okay. DPI means 1 plus, okay, the minimum of DP I minus 1, right? So that's the I minus 1 and DP like I divided 1/3 of the I. I mean, if, right, if I is like of 3 equals to 0, okay? And the last one is DP like I, the half of the I here, if I is divided, can be divided by, sorry, by 2 here. And then we get a minimum of them. Okay, so I think this top-down uh, DP state transition function shouldn't be that hard to come up with, right? So every time at the current I, since we're doing something, right, and then we're removing one, and then we just hands everything else to the to the remaining DPs. Okay, but this is the problem, right? Same thing for the BFS search, but for the BFS search, it's fine because I have already show you guys because we have other smaller numbers that can help us to finish our loop earlier. But if we're using like a recursion call, like this one, we can't, right? Because every time this DP, it will go inside the DP I minus 1, even though we have some smaller numbers here, but still here, it's gonna end up in the infinite loop. Sorry, not infinite, but it's gonna basically loop through all the numbers here, right? From a huge number, and we'll be decreasing one by one. And this will make us TLE. So which means we cannot use DPI minus 1. We have to find a way to remove it. Okay. And here, this is why making this problem a hard problem. How can we remove this DPI minus 1? I didn't come up with this solution during the contest, but maybe you guys can think of, right? So the way we're doing this is can we, I mean, basically, as you guys can see here, we are only doing the DPI uh, 1/3 of I whenever the I can be divided by 3. But instead of doing this, what we have another options here. Basically, we're using like a greedy method because we know the 1/3 is 2/3. It's obviously better than the I minus 1. Okay, so that I mean we basically we should remove this one. And we should always use the DP like the 1/3 of the DP or half of the DP. But how can we um, also covering all the possible ways, right? So the way we're doing it is like we are still have the minimum, right? But instead of this check, what do? We do a DP, sorry, not DP. We do a I mod 3 plus DP I Okay, so so this is how we handle the half of the 1/3 case. See, basically with the current I, to get to the 1/3, we have to remove the mod of I divide the mod of I with 3 here. Let's say, for example, if the I is equals to 10, that's one of the example here, right? So the first time, I mod by 3 is 1. So 1 plus dp 3. See? That's how we basically how we are converting uh all the possible numbers into like a either like dp 1/3 of I or dp half of the I. I mean, this is like a little bit like a greedy concept here. Basically, we're always trying to reduce the numbers either by a third, either by I mean by 2/3 or by a half. And so to be able to reduce the number by 2/3, we have to get to this like state first, to this state first. Okay, let me see. Yeah, I mean, like I said, we have to get to this state first because for 10, we do a flooring basically. We do a flooring with 3, and then we have a 3 here. And then for the half, right, same thing. Half is like the I is divided by 2 plus dp I by 2. So that's how we convert our state transition function here. So with this one, you guys can see we are not relying on the dpi minus 1 anymore. So basically, we're always like doing the 1/3 or the 2/3. So this one it's as if like we're skipping some of the numbers here, right? We're always trying to reach the the point that the number can be divided by 3 or by 2. That's the optimal way of doing this. Okay. And okay, so let's try to code these things here. Okay. dp and uh, so right, so this is like standard dp templates, top-down dp templates. Okay. Okay, so if right, so what's the base case? Someone may say, this okay. So here we also need to be careful here. So someone may say, okay, so when it's 0, we return 0. Okay, but will this work? I think there's an issue for this. I'll tell you guys why. So, and the answer is we're getting the minimum value, right? Okay, plus what? Minimum of n mod 3 plus dp, right? 3. The next one is the n mod by 2 plus dp n divided by 2. Okay, and then memorization dot n equals the answer. Return the answer. So let's take a look. Let's see if the n equals to 0 is our base case or not. Let's say what if this n equals to 1? Since we are doing like this, we're not having n minus 1 in this case. We're only doing like n divided by 2 or n divided by 3, right? So in the case of 2 here, so whenever n equals to 2, it will go here, right? So the 2 divided by 2 is 0, and here we're gonna have like a dp1. Okay, so how about the dp1? So let's say if we have a dp1 here, and 1 is the okay, so let's say n is equal to 1. Can we get the correct answer here? So not to 0. Okay, so let's assume. So what's the true value for n equals to 1? It's 1, right? Basically, for us to be able to eat one orange, how many days do we need? We only need 1 day because we just need one. We just finish eating this one orange at the first day. But if you're not setting that base case for 1 here, take a look here. Because here, the reason being is that for 1 here, we cannot divide it by 2 or 3. So we have to eat that one orange that day. But our solution here we're not considering that n minus 1 case. Because when n equals to 1, we have to use n minus 1 case, but we are not listing it here. So that when n equals to 1 here, let's see what we have. So we have 1 plus, so this n mod by 3 is 1. Okay. Here is dp 0 plus 0, right? It's 0. Same thing for this one. So n mod by 2, 1 mod by 2 is also 1 plus 0. Okay, so those two are both 1, and so basically 1 plus 1 equals to 2. But we're hoping to get 1. Okay, but with this like state transition functions, we are getting 2, which is wrong, right? So for that case, I mean, other besides 0 here, we also need to set initialize 1 here. Okay, right? If n equals to 1, simply return 1. Basically that's the two base case we need to set here, because again, our state transition functions does not consider the n minus 1 case. Okay, let's try to run it. Okay, submit. Yeah, as you guys can see, the DP solution is faster. It's even faster than the BFS search, because for the BFS search we still have like that one slower like slower like node that we need to process every time. But for the DP, see, every time we always decrease by 2/3 or by a half. Yeah, and yeah, see, you guys can see the code is very simple, but the idea behind the DP is not that simple. And the hard part for this problem again is to how to get rid of that DP n minus 1, right? That's the hard part. So in our case, we use a greedy idea here. We always try to go for the n divided by 3 and n divided by 2 by adding the offset here. Yeah, cool guys. I think that's it for this problem. Yeah, it's a mixed feeling. I have a mixed feeling about this problem. You know. Anyway, let me know what you guys think about this problem. Thank you so much for watching the videos, and stay tuned. I'll be seeing you guys soon. Bye bye.